The content in this presentation doesn't align with any specific section of your textbook, but it's meant to help you achieve learning objective number 13, which is to name the principal controls of temperature and use examples to describe their effects. Please plan to view this presentation before you attempt any online vocabulary quizzes or concept quizzes for the chapter. A temperature control is any factor that causes temperatures to vary from place to place and from time to time. Earlier, we looked at the most important cause for temperature variation, and that's the difference in receipt of solar radiation. Because variations in sun angle, length of daylight, and other physical Earth-Sun relationships depend a lot on latitude. They're responsible for warm tropic temperatures in the tropical regions and cold polar temperatures as we get closer to the poles. Of course, seasonal temperature change at various latitudes occur as the sun's vertical rays migrate toward and away from a place during the year. You probably, though, have heard of the Gulf Stream. That's an important surface ocean current in the Atlantic that flows northward along the east coast of the United States. A big weather maker for the East Coast. And we see a lot of different surface currents on the ocean surface, and you can imagine they have a strong influence on temperature too. The first major control, though, is latitude. It's a major control, but not the only one. If we would expect all places along the same line of latitude to have identical temperatures, we'd be wrong. It's clearly not the case. For instance, Eureka, California, and New York City are both coastal cities. We'll see a graph about those in a few minutes. And both places have an annual mean temperature of about 52 degrees Fahrenheit. But New York City is 17 or 18 degrees warmer than Eureka in July, and about the same amount colder than Eureka in January. In other words, we see a big difference in temperature based on something other than latitude. To explain those situations and a bunch of others, we have to realize that there are factors besides latitude that influence temperature. So we'll talk about those, and I'll list them here. One is the differential heating of land and water surfaces. So areas that are close or surrounded by water tend to have milder winters and warmer summers. Ocean currents. We looked at those in the intro slide, right? Altitude, also where you are on a continent, and also differences in albedo, the reflectivity of the Earth's surface. So this table, you can see that there is a considerable difference in annual temperature in the water-dominated southern hemisphere compared to the land-dominated northern hemisphere. We can also see a bunch of different latitudes represented here with very different temperature regimes. Let's look at differential heating. We already talked about how the heating of the surface controls the heating of the air above it. That means that if we want to understand variations in air temperature, we first have to learn about the variations in the heating properties of the different surfaces that Earth presents to the sun. So soil, water, trees, ice, all those have different heating characteristics. So different land surfaces reflect and absorb varying amounts of incoming solar energy, which in turn cause variations in the temperature of the air above. The greatest contrast, however, is not between different land surfaces, but between land and water. So the figure in this slide illustrates that idea nicely. It shows a satellite image of temperatures in portions of Nevada and California and the adjacent Pacific Ocean on an afternoon in early May of 2004. This was a springtime heat wave. You can see land surface temperatures are clearly higher than water surface temperatures. The image shows the extremely high surface temperatures in dark red. Surface temperatures in the Pacific Ocean are much lower. The peaks of the Sierra Nevada are still snow-capped, and so they form a blue line down the eastern side of California. For side-by-side bodies of land and water, land heats much more rapidly and to a higher temperature than water will. It also cools more rapidly and to lower temperatures than water. Variations in air temperature, therefore, are much greater over land than over water. Several factors are responsible for the different cooling rates of land and water. First is the mobility of water. As water is heated, convection distributes the heat through a considerably larger mass. Daily temperature changes occur to a depth of up to 20 feet over water. And on an annual basis, oceans and deep lakes may experience temperature variations through a layer that's between 600 and 2,000 feet thick. Heat doesn't penetrate deeply into soil or rock. It remains near the surface, and of course no mixing can really occur on land because the materials aren't fluid. Instead, heat has to be transferred by conduction from one molecule to another, and that's a very slow process. Consequently, daily temperature changes are small below a depth of about 4 inches. Although small changes can occur to a depth of about 3 feet, but those thicknesses are much smaller than the thicknesses we just described over big lakes and oceans. Annual temperature variations usually reach depths of 50 feet or so. So that's the difference in temperature from winter to summer, but not a daily difference. As a result of the mobility of water and the lack of mobility in the solid earth, a relatively thick layer of water is heated to moderate temperatures during the summer. On land, only a thin layer is heated, but to a much higher temperature. During winter, the shallow layer of rock and soil that was heated in summer cools very rapidly. Water bodies, in contrast, cool slowly as they draw on the reserve of heat stored within. As the water surface cools, vertical motions are established. The chilled water surface, which is dense, sinks, and it's replaced from below by warmer water, which is less dense. Consequently, a larger mass of water must cool before the temperature at the surface can drop appreciably. Okay, the second reason, and this won't take as much breath, the second reason why there are differences in heating of land and water is because light cannot pass through solid earth materials like soil and rock. Heat is absorbed only at the surface. So just think about how hot sand on the surface of the beach, on a summer day, you move quickly across the hot sand because it hurts your feet. Once you dig under the surface, just a few centimeters, the temperature is much lower, right? So because water is more transparent than earth, it allows more solar radiation to penetrate to a depth of several meters. So a third reason why there's such a difference in cooling rates between land and water has to do with a chemical factor called the specific heat. And that heat is the amount of heat needed to raise the temperature of 1 gram of substance by 1 degrees C. So if you want to think of it in sort of an imaginary lab, we have a gram of water and a gram of rock in 2 different beakers in a laboratory. What do we have to do to get the temperature to raise by 1 degree C? So the specific heat is more than 3 times greater for water than for land. So considerably more heat is required to raise the temperature of water as compared to the same amount of land. The fourth reason why we have differences in heating and cooling is that evaporation, which is a cooling process, from water bodies is much greater than from land surfaces. So energy is required to evaporate water, and when energy is used for evaporation, it's not available for heating. So all these factors collectively cause water to warm more slowly, store greater quantities of heat, and cool more slowly than land. Monthly temperature data for 2 cities demonstrates that the moderating influence of a large body, water body, and the extremes associated with land temperatures are easily visible in a simple chart that we'll practice constructing in lab. Vancouver, British Columbia, is a maritime city located along the windward Pacific coast. So that means it's on the side of the continent that faces into the wind. Whereas Winnipeg, Manitoba, is in the middle of the continent, pretty far away from major water bodies. Both cities have about the same latitude and will therefore experience this very similar sun angles and lengths of day. But Winnipeg has a mean January temperature that is 36 degrees Fahrenheit lower than Vancouver's. Conversely, Winnipeg July is a little bit higher, about 5 degrees higher than Vancouver. Even though their latitudes are nearly the same, Winnipeg doesn't have the marine influence, and so it experiences a much greater extreme than Vancouver does. So the key to Vancouver's moderate year-round climate is the Pacific Ocean, and that's kind of the same thing for Seattle and Everett. When we look at St. Louis compared to Ponta Delgada in the Azores, we can see in the middle of a great big continent, St. Louis gets very hot in the summer and very cold in the winter months. Over on the Azores, which isn't exactly in the middle, but it's completely surrounded by the Atlantic Ocean, we can see a very mild winter, right? Gets into the high 50s maybe, and only in the mid 70s during the summer. So nowhere near as hot as St. Louis in the middle of the summer, and nowhere near as cold. So this is a temperature range of 50 degrees Fahrenheit in St. Louis, and only about 14 degrees Fahrenheit in the Azores. Both of these about the same latitude, right? On a different scale, the moderating influence of water can also be demonstrated when temperature variations in the northern and southern hemispheres are compared. The views of Earth in this figure show the uneven distribution of land and water over the globe. Water covers 60% of the northern hemisphere. Land represents the remaining 40%. However, the figures for the southern hemisphere are 80% water and 20% land. And that shows you why it's correctly called the water hemisphere. Between 45 degrees north and 79 degrees north, there's actually more land than water, whereas between 40 degrees south and about 65 degrees south, there's almost no land. Remember the table from the first slide? This is why those annual temperature ranges are so different between the southern and the northern hemispheres. At the water surface, where the atmosphere and the ocean meet, energy is passed from moving air to the water through friction. As a result, the drag exerted by winds blowing steadily across the ocean causes the surface layer of water to move. So major horizontal movements of surface waters are closely related to the circulation of the atmosphere, which in turn is driven by unequal heating of the Earth by the sun. Surface ocean currents have an important effect on climate. For Earth as a whole, the gains in solar energy equal the losses to space of heat radiated from the surface. When most latitudes are considered individually, though, this isn't the case. Remember, there's a net gain of energy in the lower latitudes, and there's a net loss at higher latitudes. We talked about that when we were discussing the Earth's heat budget. Because the tropics are not becoming progressively warmer, nor are the pole regions becoming colder, there has to be a large-scale transfer of heat from areas of excess to areas of deficit. The transfer of heat by winds and ocean currents equalizes these imbalances. So ocean water movements account for about 1/4 of the total heat transport, and winds account for the remaining 3/4. The moderating effect of poleward moving warm ocean currents is well established. The North Atlantic Drift, an extension of the warm Gulf Stream, keeps wintertime temperatures in Great Britain and much of Western Europe warmer than you would expect for their latitudes. London is farther north than St. John's, Newfoundland. Because of the prevailing westerly winds from the west, the moderating effects of climate are carried far inland. Berlin, at 52 degrees north latitude, so further north than we are, has a mean January temperature similar to that experienced in New York City, which lies 12 degrees further to the south, 40 degrees. The January mean in London at 51 north latitude is 8 degrees higher than it is in the New York City. In contrast to warm ocean currents like the Gulf Stream, the effects of which are felt most during the winter, cold currents exert their greatest influence in the tropics or during the summer months in the middle latitudes. For example, the cool Benguela current off the western coast of southern Africa moderates the tropical heat along that coast. Walvis Bay, which is at 23 degrees south latitude, is a town adjacent to the Benguela current. And it is 9 degrees Fahrenheit cooler in the summer than Durban, which is 6 degrees latitude farther poleward, but on the eastern side of South Africa. The east and west coasts of South America are another example. This figure shows monthly mean temperatures for Rio, which is influenced by the warm Brazil current, and Arica, Chile, which is adjacent to the cold Peru current. Closer to home, because of the cold California current, summer temperatures in subtropical coastal Southern California are lower by 6 degrees than they are on the west coast. Ocean currents are responsible for the dramatic difference in annual temperature range for San Francisco and Richmond. Remember from the temperature data presentation that we looked at these two cities, which have the same average temperature and are at the same latitude. Richmond has much higher summer temperatures than San Francisco because it's adjacent to the warm Gulf Stream, and much lower winter temperatures because, well, firstly, because the effects of the Gulf Stream aren't felt so much in the winter, but also because San Francisco is adjacent to a cool, not cold, Pacific gyre. Remember that temperatures decrease with an increase in altitude in the troposphere, and as a result, some mountaintops are snow-covered year-round. This can even occur in the tropics if the mountains are high enough. The two cities in Ecuador mentioned in this diagram demonstrate the influence of altitude on mean temperature. Both cities are near the equator and relatively close to one another, but the annual mean temperature at La Paz is significantly lower than that at Concepcion. When we look at the topography here, we realize that La Paz is way up high in the Andes at 13,000 feet, and that Concepcion is low in the rainforest. So not only do temperatures drop with an increase in altitude, but atmospheric pressure and density also diminish. And because of the reduced density at high altitudes, the overlying atmosphere absorbs, reflects, and scatters a smaller portion of the incoming solar radiation. So consequently, with an increase in altitude, the intensity of solar radiation increases, resulting in a relatively rapid and intense daytime heating. Conversely, rapid nighttime cooling also happens in the high mountains. And so those stations located way up in the Cascades, for example, have a much greater temperature range than weather stations at lower elevations. The geographic setting is important because coastal locations where prevailing winds blow from the ocean onto the shore, a windward coast, experiences considerably different temperatures than does a coastal location where prevailing winds blow from the land towards the ocean, which is a leeward coast. In the first situation, the windward coast experiences the full moderating influence of the ocean. Cool summers, mild winters. And that should sound familiar to us in the Pacific Northwest. Unlike the inland stations at the same latitudes, A leeward coastal situation has a more continental temperature regime because the winds do not carry the ocean's influence onshore. So in this diagram, we can see Eureka, California, and New York City. And they illustrate that aspect of the geographic position. The annual temperature range in New York City is 35 degrees greater than Eureka's. So Eureka is right here in the bullseye for these warm prevailing Pacific winds. New York, we'll see winds going offshore in that direction. And so it is subject more to the continental climate regime. Seattle and Spokane illustrate another aspect of geographic position. Mountains act as barriers to weather. So although Spokane is only about 200 miles east of Seattle, the Cascade Range is between us. Consequently, the Seattle temperatures show a very marine influence, whereas Spokane has a continental climate. Spokane is about 12 degrees cooler than Seattle in January and 7 degrees warmer than Seattle in July. The annual range at Spokane is about 20 degrees greater than in Seattle. The Cascade Range effectively cuts us off from Spokane and cuts them off from the moderating influence of the Pacific Ocean. We already said that albedo is the fraction of radiation reflected by an object. Solar radiation reflected back to space is lost to Earth and doesn't play a role in heating Earth's surface and atmosphere. So any increase in albedo reduces the amount of energy available to heat the atmosphere. Conversely, a decrease in albedo means an increase in the quantity of energy absorbed by Earth's surface and available to heat the atmosphere. Cloud cover affects daily temperature range. This is just an albedo effect. You may have noticed that clear days are often warmer than cloudy ones in the summertime, and that clear nights are usually cooler than cloudy ones. This demonstrates that cloud cover is another factor that influences temperature in the lower atmosphere. Studies using satellite images show that at any particular time, about half of our planet is covered by clouds. Cloud cover is important because many clouds have high albedo and therefore reflect back to space a significant proportion of the sunlight that strikes them. By reducing the amount of incoming solar radiation, daytime temperatures will be lower than if the clouds were absent and the sky were clear. As noted in previous presentations, the albedo of clouds depends on the thickness of the cloud cover and can vary from 25 to 90%. At nighttime, clouds have the opposite effect than they do during the daylight. They absorb outgoing long-wave radiation from Earth and emit a portion of it towards the surface. Consequently, some of that heat that otherwise would have been lost remains near the ground. Thus, the nighttime air temperatures do not drop as low as they would on a clear night. The effect of cloud cover is to reduce the daily temperature range by lowering the daytime maximum and raising the nighttime minimum. And that's illustrated nicely in this figure. The effect of cloud cover on reducing maximum temperatures can also be detected when monthly mean temperatures are examined for some stations. For example, each year much of southern Asia experiences an extended dry period during the cooler low sun period. That's followed by heavy monsoon rains. That pattern is associated with monsoon circulation, and we'll talk about that in later on in the course. But this is a graph for Yangon, Myanmar, also known as Rangoon to some of us who have been around a little bit longer. We used to call this country Burma. This graph shows us the cloud pattern associated with the monsoon. So notice that the highest monthly mean temperatures occur in April and May before the summer solstice, rather than in July and August, as normally occurs at most stations in the Northern Hemisphere. And that's because during the summer months, when we would usually expect temperatures to climb, the extensive cloud cover increases the albedo of the region, which reduces incoming solar radiation at the surface. As a result, the highest monthly mean temperatures occur in the late spring, when the skies are still relatively clear. The influence of snow and ice is also a dramatic one on Earth's effective on Earth's albedo. So it's not just cloudiness that can change Earth's albedo. We can get a measurable change in the temperature when we measure the extent of snow and ice covered surfaces, because they also have very high albedo. This is one of the reasons why mountain glaciers don't melt away in the summer, and why snow may still be present on a mild spring day. In addition, during the winter, when snow covers the ground, daytime maximums on a sunny day are cooler than they otherwise would be, because energy that the land would have absorbed and used to heat the air is reflected and lost. Large portions of the Arctic Ocean are covered by sea ice, frozen seawater, that floats because it's less dense than liquid water. As you would expect, the area covered by sea ice changes with the seasons, expanding in the winter and contracting in the summer. Monitoring since the late 1970s has shown that over the years, the area covered by sea ice is shrinking. So broad zones that were once covered by highly reflective ice are being replaced by darker ocean surface that reflects less and absorbs more. If you think about that lowering albedo in the Arctic, it is likely contributing to rising temperatures in the whole region. And we'll talk about that topic more when we get into climate change later on in the course. So use this content and the content provided on the Canvas site, as well as the outside internet sources, to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape for the first midterm. If you can't, review the textbook, rewatch the video, and see if your ability improves. If you're still completely stumped, of course, start a discussion on the Canvas site or ask me for help.